to what we're doing today. I one of the things that I realized when I started teaching was that I knew geometry less well than all the other subjects. Almost anything else, I was ready to like stand in and teach a much more interesting lesson than what would be in the curriculum, go much deeper. And then with geometry, I realized that I had to actually go back and relearn a lot of the basics. In order to do geometry at a high level. For instance, when I came back to geometry, I didn't remember, for instance, how to prove the existence of the orthocenter. Even though that was something that like now it seems like, now that I've retaught myself geometry, it seems like a relatively simple proposition. But I found lots of people who were very good at mathematics who, if they learned it, they forgot it later because maybe they weren't taught the right perspective to really make it stick. And we all know that's true. We all know that we've learned areas of math better than others, that we've had to go back second times around because we didn't get the best perspective the first time around. So this lesson it flows out of what I noticed over time as the best perspective. And aside talking about myself, I'm going to mention a second story that actually made me really want to build a more sophisticated lesson for all of this, which was that I interviewed a student, real bright guy, a student from Yale, who I'm talking near perfect grade point average, double majoring in math and computer science. Yale was a state champion mathlete. And when I asked him, how do you know that there are 180 degrees in a triangle, he couldn't give me an answer. And it sadly, it didn't shock me as much as as much as it probably should. But mostly because he went to the same high school I did, and I know that the geometry books we used were terrible. So yeah, here we are. A lot of kids, do get this just fine. They're taught it the right way from the beginning. But it starts with parallel lines. And even before I start drawing on this triangle and walk through how we know that there are 180 degrees, I'm going to mention a little bit of the history, like Euclid's Elements, which I've read part of, but not all of. I don't know how. Has anybody else here read any of Euclid's Elements?
Part of it.
You have read? Okay, so like the very first book in Euclid's Elements goes through the first 5 postulates, or what we call the first 5 postulates of Euclid. They're the first one. The fifth one is the parallel postulate, and it's the most sort of interesting and crucial of them all. It's the one that gets debated in various ways, and then eventually, we get to Einstein and others, in an era of redefining geometry and deciding that there were non-Euclidean geometries, that we didn't have to use this postulate the way that it was stated. And yet it seemed so natural that mathematicians were trying to prove this postulate for 2,000 years. And a lot of them held hope that the first 4 of Euclid's postulates were themselves strong enough to prove the 5th, which is the parallel postulate. So first, I guess I'm gonna actually I'll go ahead and erase this picture just for a moment. I'll put it on the next page. 2 postulates involving parallel lines. I'll explain the first one, and then I'll explain the parallel postulate. The first one, anybody who's taken a geometry class has seen this at some point in time. We have parallel lines and a transversal. And this gives us a whole bunch of equal angles. Actually, I'll even do that in a second color. And yeah, it's not something that we tend to think of as proving. We could establish axioms in such a way that we did prove it, but it's not something we usually think of trying to prove. We just, it's like shooting a rocket through 2 layers of clouds. It seems right. It's hard to imagine that it would be wrong until we start, maybe go into things like warp space or something. I don't know. I'm also gonna make this mention before we go any further, because I've used both words. There are postulates and there are axioms, and what is the difference? So this is funny. Nobody in my entire math education ever taught me the difference, and here we are, several math degrees between everyone. I think, as far as I can tell, postulates is just a traditional word in geometry for axioms. That, you know, really and truly, that you know, axioms are assumptions. Or, I mean, that's the word we use everywhere. We just keep using postulates because of the history of the word. Has anybody ever seen anything that contradicts what I just said? Okay, I
No.
didn't think so. I'm pretty sure that that's basically the beginning and ending of the story. And it's one of those things, though. It's a good story to know, because I know that this is one of the things about mathematics that is confusing and terrifying to people, right? You know, basic things that that get passed down, or, you know, dilemmas over how to interpret 0 to the 0th power. You know, you know, all these things are a little bit weird at the details, and they can't be dismissed easily. So now then the second postulate, the actual parallel postulate. When I say actual, they're both actual, but just meaning the one that we gave this name. If we have a line and a point not on that line, then there is exactly one line that goes through that point that is parallel to the original line. And so we're saying that that green line, it both exists, and I shouldn't have done that, but
I like
mathematicians
that.
use yeah, mathematicians use the backward e for exists. It exists and it's unique. And we define Euclidean geometry by keeping this axiom, and non-Euclidean geometry by altering it or abandoning it. So, but this axiom is the one that guides us in doing something like a simple proof for why there are 180 degrees in a triangle. We're going to do some more complicated ones, but we'll start with this one. Everybody needs to know this if they're going to know how to make use of classical geometry. Start by identifying a line, just a line in a diagram, right? We have a postulate that involves lines. So we identify a line, the line that goes through B and C. And then we think, well, what is a point not on that line? Well, there are a lot, but there's one that's particularly interesting. And we know by the parallel postulate that through that point, there is a line parallel to BC, one and only one. And then, because of our other postulate, up there, we have statements about angles. We have these alternate interior angles and another pair of alternate interior angles. And then finally, we can see that all three angles of the triangle are up at the top and form a straight angle. And even back when you go through like the ancient texts of mathematics, they often use verbiage like the angles of a triangle are a straight angle. Just they would just say it that way. At some point, I guess 360 degrees became the way to talk about a full circle, because it's so divisible and nice and actually close to the number of days in a year. So we could think about our revolution around the sun. But yeah, so that's it. That's the proof of why there are 180 degrees in a triangle. I'm curious, did anybody learn this in geometry and then not know how to do it a year or two later?
I actually just cut out all the angles and made a straight line, and that always stuck with me because I think it was physical.
Okay. And it may have just been that my geometry education, it was actually abridged. I did half a year of geometry, but the whole thing was terrible. Anyway, so then what are other things that we can do? What things that we can understand, just completely absorb once we start looking at diagrams and thinking, what's an interesting line and an interesting point not on that line? It leads us to begin running experiments. And we're going to do the angle bisector theorem. And I think that it's funny. When I was young and learning mathematics, I thought, that's an interesting theorem. Who would come up with something like that? Was it over lots and lots of observations? And then, I learned it without proof. I'm sure I did the proof as an exercise, but it didn't stick with me. And this is why again. But let's say that we've got any old triangle. And I go, well, what's an interesting line? Well, that's an interesting line. Actually, no. That's not the way this goes. I didn't finish drawing the diagram. I got my head into another problem. Let's draw an angle bisector. And I'm just going to kind of draw it going off to infinity. It's fine. We'll call the point of intersection with BC, we'll call it, not B, but D. Okay, now we go. What's an interesting line and a point not on that line? And we could choose BC. And if we did, it just wouldn't go in any interesting place. And we go back to the drawing board, and then we might choose AC or AB. And I'm going to choose AB. And then a point not on that line, C, and draw a line through C parallel to AB. Okay. And then we start, we go, well, that's equal angles again. We like that. Parallel lines give us equal angles. We should always be thinking about that when we're doing geometry. And let's see, what else? Oh, well, we had an angle bisected up there. And so suddenly we realize we have one new observation. What's our new observation? And I'll highlight the angles.
You've created a similar triangle?
We're going to focus on the similar triangle second. I was going to mention first we have an isosceles triangle. But yes, okay, we have these two things. I don't know if I should think of one as coming first. Yeah, probably not. But ACE is isosceles, because we had two pairs of equal angles that led us transitively to make that observation. And this is going to be a key observation in what we do next, which is to identify the similar triangles. So we have angle A, same as angle, or I shouldn't say angle A, bad form. Angle BAD equals angle CED, and angle DBA equals angle DCE. I didn't mark that right, did I? There we go. Okay, so by AA similarity, we have triangle BAD similar to triangle CED. And we jump to the ratios. BA over CE equals BD over CD equals AD over ED. Okay, and so, well, we might stop and go, wait, what's our goal in this exploration? Yeah, we may or may not have a goal. We may just be exploring to see what we find, but after having gone through so many proofs of these geometry theorems, one of the things that I realized is, the interesting stuff is where you have relationships sort of synthetically come back to basic information about the triangle. I say basic information, like I focus on the ones here that have, AB is right there. And then, oh, wait a minute. AB is right there. Well, we also have, BD and CD, which make up one of the sides of the triangle. But you know what? The CE down here, the one that doesn't quite fit into that club, we know that CE equals AC due to that isosceles triangle back there. And so we can replace that with something that is interesting from the original triangle. And we're basically done now. We can rewrite the letters however we want. AB over AC, say a ratio of the two sides is a ratio of, I always call these their shadows, but we could rewrite this if we wanted. We could say AB over its shadow is equal to AC over its shadow. And so, yeah, either of these, as far as I'm concerned, are perfectly reasonable way to express it. I think the second one is the one that's usually printed in the textbook. Is that right?
Yeah.
Yeah, okay. So we'll call that one the angle bisector theorem. And a lot of times, even before I go through this, what I tell students is, imagine there's sun shining overhead, and you've built your teepee, and a ray of light comes into the teepee, goes down to the floor, and as the sun moves across the sky, there's a point at which it bisects the angle, that ray of light coming in. And that's a point at which each of the sides are in proportion to their shadow.
I like that.
Yeah, so another really good theorem, extraordinarily useful theorem. I mean, if there are 180 degrees in a triangle may be used as much as anything in geometry, but this has got to be among the more useful theorems. And so next one, we just made use of AA similarity, and that was one that becoming older, getting into my 20s, and then going back and going, hey, I'm going to be a math educator. I didn't remember how AA similarity worked. And this was a proof that I learned then, and I don't remember whether or not I had learned it in my traditional geometry education. I'm guessing not. But let's say that so you're playing with one of your kids or a niece or a nephew, and you're cutting out triangles. You have triangles with two different triangles with some equal angles. And here's the big one. And then we're going to place the smaller one kind of a snug fit where they share an angle. We're going to just place it on top of the big one, fit them snugly there, and then we go, well, these angles are the other two that are equal. Could be on the other side. It's a mirror image if it is. So we don't lose any generality. So now let's see, A, B, C, D, E. We go, well, what can we do? Well, we have equal angles, corresponding equal angles. So we have parallel lines. Okay, parallel lines give us, oh, these angles are equal also. I don't know if we care. Well, what are we trying to demonstrate? We want to prove similarity, which means that, well, we've got the equal angles. We need to show that the sides are in proportion. So this is our goal. Actually, I'm going to go bigger to smaller because I feel like, it's funny, you can do the math either way, but I feel like every time I do it, I wind up with the bigger to the smaller. And then I go, well, if you flip this. So I'll try to reframe my work with the goal. We're more immediately going to do this. So AB to AD, well, what would that do? AB and AD are on a line. And I'm realizing right now, I don't think it occurs to me, I don't actually think we're using the parallel postulate in this proof. Like we're just making use of parallel lines. And and that may be fine. It may be good. It may be that this helps express how important it is to become familiar with parallel lines, even though we're not going to employ this one key tool. It actually wasn't on my list, and I thought of it because of the last problem. But okay, we look at this and we go, okay, we've got lengths along a same line. Bigger length, smaller length. And when we have lengths along the same line like that, very often we think in terms of like same base, same height. Like that height is the height of both triangle ADE and ABE. So what we know is area of ABE, the area of ADE is equal to AB over AD. AB and AD are the bases of the triangle, and then they have the same height right there. Well, similarly on the other side, we have ACD is to AED, or I'll just say ADE, is equal to AC over AE. Okay, so we've got these two right here, and if we can connect them through those areas, then that's sufficient. So while they have the same denominator, so really we're asking, can we prove that ABE is equal to ACD? Can we prove that? And one thing that, these have some shared overlap area. So we can rewrite ABE as ADE plus DBE. ADE plus DCE. And of course, we can subtract ADE out from both sides. So all of this proposition just boils, or not the whole thing, but a big piece of it boils down to asking if these two triangles are the same. And now we're focused on a pair of parallel lines. And we have two vertices that are the same with two triangles. But whether it's that triangle, that triangle, that triangle, that triangle, that triangle, all those triangles have the same height. And they have the same base, DE. So yes, they're equal. So AB over AD is AC over AE. And that gets us this far. So how do we get this far? If we can relate it to either of the first two, and maybe piggyback off of what we've done, if we can walk through the process again, but what would enable us to walk through the process? What was our setup? We had these two cardboard triangles. We were playing with the kids and we put them together.
Oh, slide it into a different corner instead of the top corner?
Yeah. Angles D and B were the other ones that we said we knew from AA. So yeah, we slide D to B, and then we still have parallel lines, AA and AC, and we go from there and do the same thing. And that's nice. And what I really like about this proof too is that it's one of those that gets us a little bit more used to shifting areas. And I can't remember who, there was a mathematician that has a really good quote about, something about like the movement of dimensions, movement of like lengths and areas and volumes, metrics between dimensions is just sort of unique in its own kind of way. and that helped me, personally to see geometry more easily, more fluidly. All these types of techniques began to feel more natural because of it. But there, yeah, we didn't use the parallel postulate, but parallel lines were pretty important to us. So now I'm going to do, this one's the real grand one. This is the one that actually, I think it really brings home the lesson, and what we can do with it is we're going to prove the existence of the orthocenter. And which one is the orthocenter?
The intersection of the altitudes.
The intersection of the altitudes. And ortho helps us remember that if we know our prefixes. So ortho means something that's like perpendicular, like you go to the orthodontist and your teeth are sort of, I guess, perpendicular to your face. So here we are. We want to prove, and this one we call H because O is already taken. Usually call O just the center of a circle or circumcenter. But we're gonna, in this proof, we are gonna piggyback off of the existence of the circumcenter. So I think we have time actually. We've got about half an hour to work with. Let's go ahead and do that. Let's go ahead and walk through the existence of the circumcenter just so that we have the whole thing proved. And part of the reason, it's hard to imagine why the two of these things would be the same ultimately, because the circumcenter is where we take the perpendicular bisectors, and those wind up intersecting at a point somehow spectacularly. Little to the left, little to the right. No, they just perfectly thread the needle between where the other two intersect. So yeah, there's something going on here. The proofs wind up being in many ways the same, but the circumcenter is the easier one to get to. So, well, let's see. Circumcenter deals with perpendicular bisectors. So let's talk about those. We have these 2 points A and B, and any point not, well, any point on the perpendicular bisector of AB is equidistant from A and B, and vice versa. It's an if and only if theorem. I'll write that just propositions down. If we call this point C, then two propositions are the same. C is on perpendicular bisector of AB. And the second statement is AC equals BC. And this is sort of philosophically wonderful, because this is maybe the first place in a good geometry education where we see two statements that are worded very differently that are equivalent, and we're going to prove them to be equivalent. So yeah, 1 implies 2 and 2 implies 1. That's what we're saying here. 1 if and only if 2. So let's start with C being on the perpendicular bisector of AB. Then we draw to A, we draw to B, and we say, oh, look, we have side angle side similarity, because CD is equal to itself, and one right angle means we have the other right angle, and so by SAS, we have congruent triangles, and then because of those congruent triangles, AC and BC are equal. And I go through this slower with middle school students, of course. And then if we start with proposition 2, but I know everybody here has taken a geometry course before. We start with proposition 2 and just say, hey, AC equals BC. We go, well, you know, identifying a midpoint might be useful. That gives us equal stuff. And then drawing a line, we saw this equal to itself earlier, and we go, oh, well, we have side, side, side. Side, side, side means we have equal angles, and since those two equal angles add up to 180, they must both be 90, which means that CM is the perpendicular bisector. So statement 2 implies statement 1. So statement 1, statement 2 are equivalent. And then we're going to use this in a beautiful way to prove the existence of the circumcenter. We're going to go between these equivalent types of statements one way, and then turn around and go the other for the third. So let's see. We start with any old triangle. Which we pretend that we're good at making look sufficiently scalene. And we say, okay, perpendicular bisector, and perpendicular bisector, and to the extent that it looks right or wrong, we pretend. And we go, okay. I'll call this one D. No, we usually call this one D. And this one E, and that one F. And so we say, okay, what do we have here by drawing these perpendicular bisectors? So, well, maybe we shouldn't have drawn all three. That's a lot of information. Maybe we should start with 2 and say, well, we know they intersect at a point. And so we're starting with statement 1. And so what we know then from statement 1 is that this point here, which we'll call O, we know that by being on the perpendicular bisector of AC, we'll call that L. By being on the perpendicular bisector of L, we know that O is equidistant from A and C. Statement 1 implied statement 2. Similarly, it's on this perpendicular bisector, which we can call K. O is on K also. And from that, we know that OB is equal to OC. And then by transitivity, OA is equal to OB. And now we get statement 2 implies statement 1. We go from OA equals OB, and what that implies for us is that O is on the perpendicular bisector of AB. So 1 to 2 twice, 2 to 1 back again to connect all that information. So I'll go ahead and draw that perpendicular bisector back again. Yay, goes through O. If we make a big fat point. So, okay, we know that the circumcenter exists. We know that for any triangle that we draw on a plane, that there is some point, that there exists a point where all the perpendicular bisectors of the sides meet. And it's equidistant from all the vertices, which is nice. We call it the circumcenter because that equidistance to the vertices means it's the center of a circle that goes through the vertices, the one circle in which that triangle's described. So just to mention, the proof for the existence of the incenter is very similar to this. We use a different if and only if theorem, but as far as the logic goes, it's exactly the same application of that if and only if theorem. So if you can master one, it's not much of a stretch to really have both mastered at that point. The orthocenter is different, however. And I'm gonna grab a picture that I prepared ahead of time and just say, hey, we did something earlier, and if we do something and it works for us, it's perfectly reasonable to do that thing over and over again. We drew a line parallel to a side of a triangle, and we labeled a bunch of equal angles, and we had a proof that the angles of a triangle were 180 degrees. But what if we didn't stop drawing lines? What if we drew not just, through one vertex parallel to the line that makes the opposite the other two, but do that for each vertex and side opposite that vertex? And then we get this diagram. And we have 3 pairs of parallel lines now: the red, the green, and the blue. And we've identified some of the angles. I'll draw in some others. Let's see. Those are all angle C. Then we've got angle A is here. That's AB and CY are parallel. And maybe I'm doing that quickly. I probably shouldn't do this too quickly for anybody who might watch the video later, but the red parallel lines, AB is a transversal of that, and so that is the same as that angle A up at the top. And then, wait, there's one more angle A, is there? Did I just mark 2? Oh, there's angle X down here. And what's our, the blue parallel lines. I mean, the angle X is equal to angle, the ZBA, excuse me. And then finally, we chase down all the ones equal to angle B. And well, this one must be angle B because it's the third of 3 angles that add up to 180. We could just make that argument for everything that remains if we want, but we could also identify them from the parallel lines. But here we are. We fill it all out. And we go, well, there's a lot of stuff here that is the same, a lot of equal angles. Not only equal angles, but equal sides as well. We know that the 4 little triangles and the big triangle, they're all similar to each other, all 5 of those triangles. Now, the 4 little ones, we start to realize when we look closer, oh, well, between any 2 of them, they're sharing a side, right? So those, ACY and ACB, around that side, they have the same angles, and they share a side in the right corresponding position. So they are congruent. Same thing with this shared side over here and this one down here. And okay, well, that means that up here, AY is the same as BC, AZ is the same as BC, XC is the same as AB, YC is the same as AB. When we make all the marks we need to make, we realize that we have midpoints. A is the midpoint of YZ, B is the midpoint of XC, and C is the midpoint of XY. And this is special. This is special because we started with the thing on the inside, not the thing on the outside. It's far, far easier to draw stuff going on further into the interior of your diagram than it is to do something that is worthwhile looking at a bigger and bigger picture. So this is special. We do this, and we have a lot of relationships to work with, but one of those relationships we call the medial triangle, and we say it this way: we say triangle ABC is the inner medial triangle of triangle XYZ, and XYZ is the outer medial triangle of ABC. We give these names to this reciprocal relationship. Usually we just say, hey, ABC is the medial triangle. It's usually the way we say it. But so here we are. We have a medial triangle. And if we stop for a moment, we go, oh, we have midpoints along sides of a triangle. Well, let's go back to that question that we were thinking about earlier. what's going on with the perpendicular bisectors. Oh, sorry, not with that. Well, excuse me, with the altitudes. If we look at the altitude from A to BC, and then the altitude from B to AC, what have I drawn? Maybe I'll start with AD. What did I just draw? With ABC, it was the altitude of ABC from A. But when we look to this relationship to tell us what is another perspective we can take on that thing that we just did, AD is the perpendicular bisector of YZ. Okay, AD is the perpendicular bisector of YZ. BE is the perpendicular bisector, that wasn't straight enough, is the perpendicular bisector of XZ. And then CF is the perpendicular bisector of XY. And what that means is that point in the middle where it appears these things meet, they do, because that is the circumcenter of the big triangle by definition. And we know that that circumcenter exists. We know that the perpendicular bisectors of the big triangle meet at a point, and those happen to be the same lines that the altitudes of ABC are on. Therefore, the altitudes meet at a point also. So and this gives us a nice little fact too, which is that the orthocenter of a triangle is the circumcenter of the outer medial triangle of that triangle, and vice versa. And so that is a perspective on why it is that understanding parallel lines, like getting in a new groove with parallel lines, just it flips that switch on for a much higher level, more in control understanding of the basics of geometry. Any questions or other thoughts to throw into the conversation? Oh, by the way, hi Kundan. Glad you could join us.
Hey, Matthew, thank you. My camera is not working today.
So oh, that's okay.
Probably next time. Yeah.
Not a worry. Glad you joined us.
No, thank you. Yeah, I'm enjoying the sessions. Yeah.
I'm glad. So anybody have any thoughts or other insights about these proofs we just walked through?
That was beautiful. It was very elegant.
Thanks. And I can assure you that when I found myself in a classroom teaching this for the first time, it was not. So I felt like it was my, I needed to come up with something to be able to better talk it through. And I could tell as I did, I spent a while, identifying each time I went through, what is it that I should have been focusing on? What would make me remember these and remember them forever? Because I didn't have to think of them as a stamp collection of facts, or memorize a bunch of proofs. And nobody ever wants to do that. What we want is to understand the ideas together as a collection of ideas, and really and truly, and it deserves to be, because the parallel postulate is that important. It is that fundamental to the way that we do things, even with modern mathematics and physics. The ways that we change it is fundamental to what happens. So it's not a surprise that when we go back to classical geometry, so much revolves around it. Out of curiosity, any problems or other ideas that might relate to this that, like, just, do you watch this and go, does this now relate to this other proof that I did once upon a time in geometry? So, okay, given that we have about 12 minutes left, and we're kind of through the point that I intended to get through, I'm going to mention that this type of thinking helped me understand a little bit better Ptolemies theorem and Ptolemies inequality. There's the equality case that we see more often, but I'm gonna build Ptolemies inequality, and it's not as dependent on parallel lines per se, It's not a proof with parallel lines. It is a proof that involves the type of thinking that we did here, which is to explore a diagram and say, what can I draw into it to generate information? That's the way I'm going to put it. Generate information as if it were out of thin air. Draw outside stuff that just may result in hard relationships.
Is
So
Ptolemy's theorem the one that involves cyclic quadrilaterals and product of
yes.
opposite sides? Gotcha. Okay.
Yes, and in fact, forgive me for this. I'm going to do a quick search for one of my diagrams because it is it's one of those diagrams that is just tough enough. Oh, come on, search, give me something better than that. Okay. I'll return to final diagram that I'd drawn all over. Oops. Okay, got a good one. Oh no, that's too much. Okay, I'll draw a more basic one first. So here's I'll call this Ptolemies Inequality, and I'll say that what this theorem says is that if we have a quadrilateral, and this is any quadrilateral, there's a version of this for cyclic quadrilaterals, but we'll get to that later. So we have this, and then we have two diagonals, and this is what the inequality says. It says the products of the pairs of the opposite sides added together equals the product of the diagonals. No, I'm sorry, not equals, is greater than or equal to, excuse me, greater than or equal to. I was jumping to the equality case, but okay, greater than or equal to. So first thing I'm going to say about this, and I don't know why this wasn't obvious to me the first time I saw this. I think, again, it's because I had to go back and rebuild my whole geometry and think about it in a new way. But the structure of this, there aren't many easy inequalities in geometry. There's one that we kind of look to as sort of the ultimate easy inequality in inequality geometry, and that's the triangle inequality. It says that the sum of two sides of a triangle is at least as large as the third. And here we have two quantities greater than or equal to another quantity. And it's kind of natural that we might suspect the triangle inequality of being involved in whatever happens here. So here we go, well, what is it that we can do with this diagram to kind of get started? And I don't know exactly where, what this idea would be or how to describe it. I think that students who have ever learned something called spiral similarity might see this more easily, but I'm going to give this a label that I know will work. If we rotate around A, and then that would rotate D to, maybe it's a little further out from B. I didn't really specify links, but if we rotate AD around A clockwise until AD is in line with AB, and then we stretch it or shrink it like a similar figure so that that new point D winds up there, and we take this triangle ACD that would have swung around this triangle right here and we swing it so that it's like that up there. It'll be the same angles but resized. And this is, it's a little bit hard to imagine if you're not, drawing it out. So here is a diagram where that's been done for us. So that's one way to think about it is rotating around A. Another way to think about it is if we want to construct an interesting point outside the diagram, an interesting point in this case, we're gonna go after equal angles, which means we're really going after similar triangles. We're trying to make similar triangles happen, hopefully. So, if we take this angle at D and then construct that angle there and just shoot this ray outward and do something at A, make that same angle BAC and shoot that angle outward until we get to a point E that's out here. So E is the new point. It's the artificial point in our diagram. And we look here and we go, well, triangle inequality, and there are a couple of candidates now. And I'm going to suggest this candidate right here. And it's not, maybe it's not immediately clear why we suggest that candidate. But does anybody notice a pair of similar triangles? We'll talk about our candidate triangle momentarily. We have some of our angles there at A, C, and D. And those same angles in corresponding order are at A, E, and B. Then we have AC over AE equals AD over AB equals CD over EB. And just looking over here, I see a couple of these links that have our point E, our artificial point that we've created. It's not really well, yeah. It is pretty artificial. Yeah, I'll keep using that word. So AE and EB. Well, EB, that's one that stands out for me. And when I look at that one, and I look at, I'll call this one the ratio of solid information. I think of it that way because those are sides of our original quadrilateral, right? That feels like something we can relate stuff back to when we need it. But once we've identified these similar triangles, there's actually a second pair that pops out. And this is the tougher one to see. We used angle similarity to identify this pair. But once we identify it, we also have ratios of lengths all of a sudden. And ratios of lengths give us the opportunity to use other similarity, SAS, for instance. Can we see another angle around which we have side information, or can we look at the side ratios that we have and maybe come up with it? This is one that really takes some time to just learn to spot ordinarily. Good geometers, people who do this stuff and make it their business, they see this just boom immediately. And if we start looking at the rays that make those angles and the triangles made up from that ACD and AEB And these two are part of that, aren't they? Oh gosh, am I doing this right?
I think you wanted ABD.
Yes. Yes, thank you.
Sure.
ABD and AEC.
ACE.
Is it EC or CE?
Oh. Shoot.
EC. That's right.
Okay. And which one of the ratios do we use from above?
The left two.
Yeah, it is left. Okay, that's what I thought. Okay. Yeah, and what we do to get them in the right order, AC over AD equals AE over AB. There we go. Thanks. Okay, and so I'm going to write these out now. AB over AC equals AD over AC equals BD over EC. Okay, so here's what we've got going. I see AE and AE, but I see EB and EC. Now this points to our candidate triangle, the EB and the EC, each listed once. And the AE turned out to be sort of transitory between the information from the similar triangles. But EB and EC point us toward saying, hey, what if we started with BE plus BC is at least as large as CE. But what we want to do is get rid of the artificial point. It's kind of like if we were to, write, similar triangles up here when we're doing the angle bisector theorem. We may go, hey, let's get rid of CE over here. And we do so by relating it back to the information we have from the original figure, from the original triangle. Doing the same thing here, we go, okay, we want to replace these. So let's start with BE, which is right here. We're going to use this. BE from that equals AB times CD divided by AD. So we'll substitute right here. Then CE. Again, we'll use these because there's just one letter E and everything else is in our original quadrilateral. We say EC, if we isolate EC, it's going to be AC times BD over AD. Oh, that's nice. The denominator of the two fractions is the same, and we just don't like fractions. So we're going to multiply that out everywhere. And we get AB times CD, which is product of a pair of opposite sides of the original quadrilateral, plus BC times AD, which is product of the other two, is greater than or equal to the product of the diagonals. And that's it. Ptolemies Inequality. And that's such a beautiful theorem. And how do we get equality? Where do we get equality in the triangle inequality?
When the triangle is a straight line.
When B is there. And once again, I'm going to cheat and use a prepared diagram because this just looks nicer. And at the point at which we have, these were angles that we used earlier. If we call that theta, then right here we have 180 minus theta. And we can see that we have opposite supplementary angles. And that is one of our equivalent criteria for saying, hey, we have a cyclic quadrilateral. So we have AB times CD plus BC times AD is at least as large as AC times BD with equality if and only if the quadrilateral is cyclic. And that's when we call it perhaps Ptolemy's theorem. All right, any questions or thoughts?
Well, I like seeing the derivation. I just seen I just had the rote fact that we learned from a formula sheet, but it's nice.
Yeah, we were, gosh, when you and I were doing math team, even a problem involving Ptolemy's theorem was kind of few and far in between, right? Unless you were doing the Olympiad material stuff, you didn't see the inequality version at all.
Right.
And so so when I started teaching, this was one of those that I'd used it enough to want to know how it worked. So actually, I think it may have been forced to. I think I had to work with a student, like just boom, one day we used to have office hours online at Art of Problem Solving, and we'd have independent studies and office hours, and somebody would come in and they might ask about anything, and what this you learn to plug gaps in your knowledge in 5 minutes at a time. So that no matter what they ask you, you can pull out a book with a proof, and then you're like, okay, well, how do I come up with the easy words to explain this? And if you don't do a good job, you kick yourself, and that makes you go home and go, I want to come up with this in plain words.